So just like what I mentioned at the end of the lecture videos of section 1.4, I will be doing this example here and also this example here before I go to our next lecture. So these two examples, it's proving, and you expect proving in exams, okay, in this course, okay? So in mathematics, our goal is to prove statements that are being used or considered, okay? So let's start with this first example. If A is invertible and we have AB equals AC, then B equals C. Okay? So recall that um, I have shown you a similar statement in here. Okay? The statement was if A, B, and C are matrices such that multiplication is possible, etc., and such that AB equals AC, it does not mean that B equals C. Okay? But if we add the condition that A here is invertible, then the equality will follow between B and C. Okay? So how is this? So proof, okay? So since A is invertible, we have um, A inverse exists, of course. We have this. A inverse exists. And what we're going to do is to multiply this A inverse on both sides of the equation since we are given AB equals AC. Okay. So we have here A inverse multiplied to AB. Then this is the same as A inverse multiplied to AC. Okay. That's just multiplication property of equality. What you do on the left, if you multiply something on the left, you have to multiply something on the right. So equality is preserved. Or if you add something on the left, you have to add the same thing on the right so that equality is preserved. Okay. So in here, what we do is we have AB. Okay. We multiply this inverse of A, and therefore AC, we also multiply the A inverse. Now, we are talking about matrices in here. Okay, so there is more um, conditions and um, properties that needs to be followed, that need to be followed. So when you are multiplying matrices, okay, when you multiply a matrix on matrices which are equal, okay, you have to preserve also or you have to make sure that the side of the factor remains or is the same. Um, how do I explain that? So, for example, you have two factors here. Particularly, you have this AB and then you have this AC. They are equal because of this um, condition or this hypothesis. Okay, so what we do is multiply A inverse of both sides of the equation. That's from the property of equality. Now, furthermore, if you multiply, if you look at the left hand side of the equality, if you multiply A inverse, okay, on the left of your factor AB, you have to multiply also the A inverse on the left of the factor AC. Okay? So, for example, again, maybe if you have matrices M equals N and you want to multiply some matrix Q, okay? You multiply this matrix Q here. What you do is, if you multiply Q on the left of M, you also need to multiply q on the left of n. Okay, and the equality is preserved. Okay, this guy here, you have say qm, you multiplied q on the left of m, and then on the other side, okay, on the other side, you have n, but you multiplied q on the right, then this equality may not hold. Okay, so again, you have equalities of matrix. You multiply a matrix on the left-hand side of the equality, you also need to multiply the same matrix on the right-hand side of the equality. That's one. But if you have matrices in here, you have to consider where you multiplied your matrix. If it's on the left of the given factor, okay, then it must also be multiplied on the left of the other side there. Okay? I hope I made that clear, but any question on that? Anyway, so we have this. We apply or we use associative property of equality, meaning we can regroup this. We now have A inverse A. We multiply that, and then we have B in here. And we do the same thing on this side of the equation. You have A inverse and then A. Then you multiply C here. But property of inverses, this guy here, this is just the identity matrix. This guy here is also the identity matrix. Okay? So we will have here IB. This is equal to IC. But again, if you multiply any matrix with the identity matrix, as long as the multiplication is valid, you'll just get the matrix. So if you multiply B with I, you'll just get B. So in here, we'll just have B, and also on the other side, we have C. And this proves our statement here. Okay? So if A is invertible and we have AB equals AC, then B must equal to C, or must be equal to C. Okay? For the next problem here, we define first idempotent. A square matrix is said to be idempotent if you square A, you get A. Okay? So a square matrix A, let me just put that here. A square matrix A is idempotent if A squared equals A. So this is what we want to prove. Prove that if A is idempotent, meaning it follows this condition, then 2A minus I is invertible and is its own inverse. Okay? So if A is idempotent, then 2A minus I is invertible and its own inverse. So how do we prove this? Well, we just need to get the inverse of 2A minus I, if possible. And once we have the inverse, then we can conclude that it's invertible. But another part of the thing, or of the statement that we need to prove is 2A minus I is its own inverse. So we have a clue what the inverse of 2A minus I is. Okay? So let's start. We have, or one has, 2A minus I. So we want to show that this 2A minus I is its own inverse. So meaning, if I multiply this 2A minus I with itself, okay, I should get the identity. Correct? Because that's the condition. A and B are inverses if AB equals I or BA equals I. Okay? So if I multiply this 2A minus I with itself, I should get the identity matrix. So maybe let's look at that. Okay? So in here you have 2A times 2A in here. So we will get 4A squared. Is that correct? Because 2A times 2A is just 4A squared. If you want to be more precise in here, okay, you have here 2A times 2A. But 2 is a scalar. So these two can move anywhere. And then you will have 4 times A, which is equal to 4A squared. So anyway, we will do that later. And then here, 2A times I, or times negative I, this becomes what? 2A times I. And then we have here minus I times 2A. So in here you have minus I times 2A. And then in here you have minus I times minus I. So we will have here plus I squared. And like I said, this scalar here can go anywhere. So we can just multiply this scalar with this scalar here. So we will get 4, and then A times A, that's the time we get A squared. 2A times I, it's just the 2A, correct? You have a matrix, you multiply it to the identity matrix, okay, or to the necessary identity matrix, and you will get the matrix back. So this is minus 2A. Here you have the identity multiplied to 2A again. So same, we will have minus 2A plus I squared. So I, you multiply it with itself, you'll just get I. So you will have here I. Now look at this. It is assumed that A is idempotent. It means that A squared equals A. So this A squared here, this is just A. Okay? So in here, since A is idempotent, okay? Since A is idempotent, A squared is equal to A. And then here you have minus 2A, so that's just minus 4A, and then plus the identity matrix. And of course, 4A minus 4A, that's just 0. So you will have the 0 matrix plus the identity matrix, and you will get the identity matrix. So what does this mean? You have two matrices multiplied to each other. In fact, you have a single matrix, you multiply it with itself. Okay, and the resulting product is the identity matrix, which means one of the factors is the inverse of the other factor. Or in this particular problem, we have 2A minus I. So let me just write it. Therefore, 2A minus I is invertible. 2A minus I is invertible. And its own inverse. And is its own inverse. Own inverse. Okay? So there's a question here, where did 4A squared go? Again, because A squared equals A, because A is idempotent, that's there. That's in the assumption. Since A is idempotent, or prove that if A is idempotent, meaning A squared equals A. So this a squared becomes a there. Okay? Other questions? Okay? So now, um, let's go to our next topic. So for this part, we will now go to section 1.5, elementary matrices and a method for finding A inverse. Okay, so in the last lecture, we defined what an inverse matrix is, and then we had a way of finding the inverse of 2 by 2 matrices. Okay, so for this lecture, we will learn another method, okay, of finding inverse of matrices. So 2 by 2, 3 by 3, 4 by 4, etc. Okay, so we will see that later. First, let us talk about elementary matrices. So remember, elementary row operations, okay? What were these? We, we have a matrix, and then the elementary row operations are the following. First, multiply a row by a non-zero constant, okay? And then second, we interchange two rows. And then the third, we add a constant C times one row to another. Okay? So for example, in here, you have a non-zero constant. So your C um, multiplied to row I or row J. Okay? You multiply this to, say, row J. This will become, okay, your row J. You interchange two rows. So you have row I, you interchange it with row J. And then here, you add a constant. So you add a constant times row J to another row. So you have here row I plus C R J. So row I plus C row J. This guy here can replace this row I. Okay? So hope you remember these three. So what do we get? For example, you have a matrix A. You do this, okay? You do either of the three or combinations, etc. Okay? But say, let us just do one of them. So we apply an elementary row operation. We get a matrix B. We change the matrix. Okay? Most probably. Of course, if you are just going to interchange two rows having the same entries, then of course the matrix will not change. Okay? Or if you multiply by one, the same row, you won't change the matrix. So um, we can just skip those guys, those operations. So in here, we are assuming that we apply this elementary row operation such that our matrix will change. But this is also true, or the next discussion, the next things that I will going to um, discuss is also true, even if the matrix won't change after applying elementary row operations. Okay? So, we have a matrix A, we apply a certain row operation, elementary row operation, and then we get a matrix B. So the question now is, how do we recover this matrix A from B? So this is what we have. Matrix A, apply elementary row operation, we get a matrix B. Now, if we start from matrix A, what do we do to get, sorry, if we start with a matrix B, what do we do to get matrix A? So, still, we will apply elementary row operations, but we will reverse the process. If we knew how we got matrix B from matrix A. Okay? So, we perform the following operations. These are also elementary row operations. So, from before, we multiply the row by a non-zero constant C. To recover the original matrix, this time we multiply the same row by 1 over C. Okay? So, for example, let's look at these examples here. For example, you have the matrix, say, 1, 2, 1, 0, 3, 1. Okay? This is your matrix A. And then we have here matrix B. We apply, say, we multiply a non-zero constant to one row. So we say 3 times row 1. The matrix B will become what? 3, 6, 3, 0, 3, 1. Correct? And then, suppose we have this matrix B and we want to recover matrix A. According to this, we multiply the same row by 1 over C. So, from this matrix B, we want to recover matrix A. We multiply the same row, so the same row 1, okay, by 1 over C. Our C earlier was 3. This time, we multiply by 1 over 3. And if you do that, you will get exactly A. So 3 divided by 3, that's 1. 6 divided by 3, that's 2. 3 divided by 3, that's 1. And then you just copy your second row here, which is exactly now is A. Okay? Next, interchange the same two rows. Okay? So before we interchange two rows, row I and row J. So to bring back the original, you interchange them again. Okay, you interchange them again. Okay? For the third one, look at this. If B resulted by adding C times row I of A to row J, then add negative C times row I to row J. Okay? So, for example, let's have this again. 1, 2, 1, 0, 3, 1. This is your A. We want to convert this to B. We look at this. Add C times row I to row J. So suppose let us change row 2 by row 2 plus maybe 5 row 1. Okay? Of course, we are just fixing row 1 here. We have 1, 2, 1. What about row 2? So we have here 0 plus 5 times 1, that's 5. 3 plus 5 times 2, that's 13. And then 1 plus 5 times 1, that's 6. Okay? So far, so good. Now, if B resulted by adding C times row I of A to row J, then add negative C times row I plus row J. Okay? So row I here, row I here, still row J is the one that you want to change. So in here, to bring back A, we add to row 2, okay, negative C times row 1. Okay? So meaning, in this case, you have minus 5 times row 1. Correct? So if we do this, let us see. Again, row 1 is fixed, so we still have 1, 2, 1. For row 2, we have 5 minus 5 times 1. So that becomes 5 minus 5. This is 0. And then in here, we have 13 minus 5 times 2. So 13 minus 10, that's 3. And then 6 minus 5 times 1. So 6 minus 5, that's 1. So notice you get A again. Okay? So these three guys here, these are the inverse process of the elementary row operation that we had in this slide here. Okay? But again, these guys here, these are also elementary row operations. Okay? These three guys here are also elementary row operations. So you can combine them. Okay? You can combine them. It's just that if you have a matrix B and you want to go back to the original matrix, okay? In a sense that if B is obtained by applying elementary row operations on the matrix A, then you reverse the process via these three statements here. Okay? So take note, from A to B, we just applied a single row operation. And of course, from B to A again, we apply a single row operation. Okay? So we define the following. Matrices A and B are said to be row equivalent if either, hence each other, okay, can be obtained from the other by a sequence of elementary row operations. So in here, you have A to B, you apply this, you can also have several elementary row operations to get a matrix B. Okay? So maybe you have matrix A, top, then you have op 1, row operation 1. So you will have some matrix in here, and then again, operation 2, okay? Another matrix in here, and then maybe operation 3, and then you'll get B. If these operations here are elementary row operations, meaning this guy here, or this guy here, or the other set, okay? Then these two matrices, A and B, are row equivalent. So if A or the other one can be obtained from the other or the one by a sequence of elementary row operations. Okay? Now, a matrix E is called an elementary matrix if it can be obtained from the identity matrix by performing a single row operation. Okay? For example, this guy here, 1005. Okay? You start with the identity matrix, okay, you apply a certain elementary row operation. For this one particularly, you just have to multiply 5 times row 2 and you will get 1005. So this guy here is an elementary matrix. From the identity matrix, apply a single row operation and you will get an elementary matrix. Okay? In here, you have 0, 1, 0, 1, 0, 0, and 0, 0, 1. You start from this identity matrix here, the 3 by 3 identity matrix, and you have row 1 interchange with row 2. So if you do this, you will get this matrix here. So you interchange these two rows. You'll have 0, 1, 0, 1, 0, 0, 0, 0, 1. So a single row operation. Okay? Another one here. 1, 0, negative 3, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So from the identity matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. So this is the 4 by 4 identity matrix. Okay? We can apply the row operation, row 1 minus 3, row 3. So rows 2, 3, 4 will change. We will not change. For row 1, you replace it with row 1 minus 3, row 3. And as you can see, you will have 1 plus 0, that's still 1. That's 1 here. 0 plus 0, that's still 0. And then 0 minus 3 times 1. That's your negative 3 here. And again, 0 minus 0, that's still 0. So this guy here is this matrix. So again, a single row operation. Applied on the identity matrix, we have an elementary matrix. Okay? And of course, the identity matrix itself is an elementary matrix. You can just multiply 1 to any row and you will get the same matrix. Okay? Questions? Okay. So now, how important these elementary matrices are? Theorem. If the elementary matrix E results from performing a certain row operation on the identity matrix, and if A, so the identity matrix here, it's an M by M matrix. If A is an M by N matrix, okay, then EA, okay, the product EA is the matrix that results when this same row operation, so this guy here, is performed on A. Okay? So first take note, the identity matrix is M by M. If you apply an elementary row operations, or if you apply a elementary row or an elementary row operation, you'll still get M by M. So E is an M by M. This matrix, it's M by N. So take note, your E is on the left, A is on the right. So let's have that. E is an M by M. A is on the right, which is M by N. So the resulting product here, it's still M by N. But take note, this is same as A. Same size as A. And according to this theorem, instead of actually multiplying EA here, all you have to do is to know what row operation was applied to the identity, okay? And then you apply that to matrix A. That's your EA, okay? So take note, if you apply some elementary row operation on A, the size will be retained. So still M by N. Okay? So to understand this further, let us look at this. You have the matrix A here, it's 3 by 4. You have a matrix E here, it's 3 by 3. And you want to find the product EA. So you can multiply them. Go ahead. But what we're going to do is to observe E. Take note that E here, this guy here, was obtained from the identity matrix. Okay? So you have the 3 by 3 identity matrix. Okay? This is your I. Okay? You apply a single row operation. What row operation was used? This is R2 plus 4R3. Correct? So we are not changing the first row. We'll just have 1, 0, 0. For the second row, we have row 2 plus 4 row 3. That's 0 plus 0. That's still 0. 1 plus 0. That's still 1. 0 plus 4 times 1. You get 4 there. Third row, you are not changing it. So this is your E. This guy here. Okay? So what about this? You want the product EA. Okay? According to this theorem, all we need to do is to apply the same operation to A. Okay? So you have the matrix A, you apply row 1, row 2 plus 4 row 3. Okay? So for row 1, it's just the same, you just copy 1. So you have 1, 0, negative 3, 2. For row 2, we have row 2 plus 4 row 3. So 1 plus 4 times negative 3. So 1 minus 12, that's minus 11. Then here you have 1 plus 4 times 4, that's 1 plus 16, that's 17 here. Here you have 5 plus 4 times 2, that's 5 plus 8, that's 13. Then here 3 plus 4 times 1, so 3 plus 4, that's just 7. And then you just copy third row. Negative 3, 4, 2, 1. So this is the product EA. So this is your E, A. Okay? Questions? So, we've seen our row operations, elementary row operations, and also the inverse processes. Okay? So multiply row I by C, which is non-zero. The inverse process multiply row I by 1 over C. You interchange rows I and J. The inverse process is the same. You add C times row I to row J. The inverse process is you add negative C times row I to row J. So now, every elementary matrix is invertible. And furthermore, the inverse is also an elementary matrix. Okay? So every elementary matrix is invertible, and the inverse is also an elementary matrix. Okay? So for example, you have this 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay? This is, say, your elementary matrix 1. Let's try to find in E1 inverse. Okay? The inverse of this is also an elementary matrix. So it's similar to how you obtain this E1 from the identity matrix. So how do we get that? From the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. This is your identity matrix. You see, you interchange rows 1 and 2. So in here, you have row 1 interchange with row 2. If you do that, you will get this 0, 1, 0, 1, 0, 0, 0, 0, 1. So this is your E1. Okay? So what did we do? Row 1 interchange with row 2. If we go back to this is what we did. Okay? This is what we applied on I to obtain that E1. The inverse, you apply this. Okay? You apply this. Okay? So it's also interchange rows I and J. Okay? So the E inverse, let's us see, is the E inverse equal to the same thing. You apply row 1 to, you apply row 1, interchange with row 2. So you'll have 0, 1, 0, 1, 0, 0, 0, 0, 1. So the question, is this the actual inverse? Let us see. You have E1 times 0, 1, 0, 0. Here is 1, 0, 0, 0, 0, 1. Okay? But according to the previous theorem says, if you know the elementary row operation applied to the identity matrix, to obtain this elementary matrix here, you apply the same row operation on the right factor to get the product. So to get E1 from the identity matrix, we did this. Row 1 interchange with row 2. which means we will also do the same thing on this right factor. And if we do that, we're just going to interchange row 1 and row 2, and we will have that identity matrix again. Okay? And therefore, E1 and this matrix here are inverses of each other. This is your identity matrix. So E1 and these are your inverses. And indeed, we have E inverse here. Okay? The inverse of an elementary matrix can be obtained easily by doing this inverse process in here. Okay? Another one. Let's have another one. Suppose we apply this guy here. Multiply row I by non-zero constant C. Okay? For example, our E1, or let's write E2 now. Suppose our E2, this is 1, 0, 3, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now we are on 4 by 4. Okay? So our goal, what is this E2 inverse? Okay? You have your I4. This is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. What elementary row operation should we apply on I4 to get E2? Anyone? So what elementary row operation that we need to apply to I4 to get E2? If you guessed row 1 plus 3 row 3, then you are correct. At least one of your classmates answered. Yes, that's the row operation applied to I4 to get E2. Okay? Um, let me correct myself. I'm doing this third row in here, not the first row. So I'm doing this third row. So this is what we do. Okay? Add C times row I to row J. The inverse matrix of that elementary matrix would be to apply this guy here. Okay? To apply this guy here on the identity matrix. Okay? So add negative C times row I to row J. So I claim that E2 inverse is the following. From I, okay? So from I4, we apply row 1 minus 3 row 3. Because from before, you have row 1 plus 3, row 3. This time, you add negative C. So you now have negative 3. So I claim that E2 inverse is the matrix. So from this, we apply here 1 minus 0, that's 1. 0 minus 0, that's 0. 0 minus 3. Correct? So you have negative 3, and then 0 minus 0, that's 0. And then you just copy third until fourth, second until fourth row. Okay? So I claim that this is the inverse of E2. So the question is this really the inverse of E2? You can check. You multiply this matrix with this matrix. Okay? This is your elementary matrix. So if we do that, let us see. E2 times the matrix 1, 0, negative 3, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. You can multiply this E2 and this matrix here if you want. Just 4 by 4 matrix times 4 by 4 matrix. You can do that. Okay? But we will apply the theorem from before, meaning I just need to apply this guy here on this matrix here, because this E2 was obtained by doing this row operation. Okay? And therefore, I just need to apply this to this matrix here. So I am invoking this theorem here. Okay? So if I know the operation applied to the identity matrix in order to get E, I'll just do the same row operation on A, and I will get the product EA. So let's do that. This is equal to, so if you tried to do this, you apply row 1 plus 3, row 3 on this matrix. So 1 plus 0, that's 1. 0 plus 0, that's 0. Negative 3 plus 3 times 1, that's negative 3 plus 3, that becomes 0. And of course, this is 0. And then you copy everything else in here. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And indeed, you have the elementary matrix. Okay? You have the identity matrix. So we're done with the first part of the verification using the definition. And in fact, I think I mentioned this before, it's enough to check one part. Okay? So what am I saying there? In the definition of identity, A, B equals I. So condition 1, condition 2, B, A equals I. So this is from the definition. Okay? And then I'm saying you can just do one of these. If you've shown AB equals I, then that's fine. Or BA equals I, then that's fine. Of course, provided A and B are of the same sizes. They are both square matrices with the same size. So you can just do one of them. So I will give the statement related to this later. But right now I'm doing it. Okay? So our claim now is proved. E2 inverse, it's given by this. So you just need to apply, this part here to get the inverse of the elementary matrix. And of course, for the first here, if you multiply row 1, say by 5, the inverse will be multiplying the identity matrix by the row 1 of the identity matrix by 1 over 5. That's what it says here. Okay? Questions so far? Now, this theorem here is very nice. Okay? So this connects the n by n matrix. If we assume A here to be an n by n matrix, and if we assume that it is the matrix of coefficients of a linear system, okay, then we will have this letter B here. But anyway, so what does this tell us? You have an n by n matrix, then these four statements are equivalent. So what does this mean? If A is true, then B is true, also C is true, and also D is true. If C is true, okay, if you start with C, then A will be true, B will be true, D will be true. In short, they are all true or they are all false. If one of them is false, everyone will be false. If one of them is true, everything or everyone will be true. Okay? So what is this? A is invertible. This equation here, AX equals 0, has only the trivial solution. There's only one solution, and the only solution is the trivial solution. If you get the reduced row echelon form of this matrix A, you should get the identity matrix. So this should answer the question of the question before. How do you get the identity matrix? Well, find the reduced row echelon form. You apply Gauss-Jordan method if you have to. But basically, what you're doing is just applying a sequence of elementary row operations. And furthermore, this fourth statement here, A is expressible as a product of elementary matrices. Okay? So A is invertible. It implies A is expressible as a product of elementary matrices. It also implies AX equals 0 has only the trivial solution. Okay? If you have a matrix A and the reduced row echelon form is the identity matrix, then this matrix A must be invertible. Okay? Now, if your matrix is not invertible, then the reduced row echelon form of A will not be the identity. Okay? So if A is not invertible, the reduced row echelon form of A will not be the identity. Okay? If you have a homogeneous linear system with the square matrix of coefficients, just like this, and this, say this equation has at least two solutions. Of course, one of them will be the trivial solution, but if you found non-trivial solutions, to this equation here, then your A is not invertible. Okay? So again, if one of them is true, everyone else will be true. If one of them is false, everyone else will be false. That's what this the following statement are equivalent means. Okay? So the theorem says that all statements are true or false. Okay? Now, you look at this. You have a square matrix which is invertible. So if you try to reduce this, okay, if you try to get the reduced row echelon form, you should get the identity matrix. Okay? This guy here, the equivalence between A and C here, is actually helpful in finding an inverse of a matrix if it were invertible. Okay? And in fact, if you have a matrix A, which is not invertible, if you try to do the same method, you won't get the identity matrix, which means you won't have the inverse. Okay? So to get an inverse of an invertible matrix, say A, we use what we call the inversion algorithm. Okay? So to find the inverse of an invertible matrix A, find a sequence of elementary row operations that reduces A to the identity matrix In, and then perform the same sequence of operations on I to obtain A inverse. So how do we do this? You have a matrix A. You apply row operation 1. So row operation 1. Apply again row operation 2. Row operation 2. You apply this all throughout. So row operation, say some K. So after you applied K row operations, and in here by row operation, I mean the elementary row operation. Okay? The three operations that we have. Okay? So you apply these operations until you get I. Okay? You will get this IN if A is an n by n matrix. But anyway, you should get this identity matrix. So identity. According to this, you apply the same row operations. So same sequence of row operations on I, you will get a inverse. So meaning, if I have I in here, and then I apply the same row operation. So for example, I have I in here, I applied this row operation 1, I'll get some matrix, I'll apply another row operation, okay? So row operation 1, I apply again this same row operation here, and I do this all throughout and apply this guy here, row operation K. I will get a matrix in here. The matrix here, that's your A inverse. Okay? So this is the inversion algorithm. So most of the time, we do this like this. We do it like this. You have the matrix A, you augment the matrix I. Or let me use the same color here. You augment the same matrix I. Remember augmented matrix? When you say you augment, you actually put the matrix there beside it. Okay? So if you apply the row operations here, okay, row operations here, you will end up with, on the left, on this part, you will end up with the identity matrix. On the other side there, what you will get is the inverse. Okay. Okay. Questions? So I think this will be better understood if we do some examples. For example, in here, find the inverse of the following matrix using inversion algorithm. So take note, inversion algorithm. So what do we do? This is our matrix A, for example. So we have this A, we augment the identity matrix. So what does this mean? You have here 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0. And then you augment the identity matrix. So the identity matrix, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So your goal is to convert this side here, okay? To convert this side here to the identity. And this will follow suit, of course. This will be some other matrix. And once you have converted this side here to the identity matrix by applying elementary row operations, the matrix on this side will be A inverse. So basically, in here, originally your matrix A, it's 3 by 3. Now you have this matrix here, it's 3 by 6. Correct? And you just want the reduced row echelon form of this 3 by 6 matrix. Okay, so let's do this. This is already a leading one on this side. This is already 0. We want to make this 0. So meaning, we will replace row 3 by row 3 minus row 1. So if we do that, in here we just copy row 1 because we are not doing anything. You have 1, 0, 1. The other side there, it's 1, 0, 0. And then here, 0, 1, 1, 0, 1, 0. For row 3, we have 1 minus 1, that is 0. 1 minus 0 here, that's 1. 0 minus 1 here, that's negative 1. Then 0 minus 1 here, that's negative 1. 0 minus 0, that's 0. 1 minus 0, that's 1. Okay? So now, this is a leading one. All the entries here are 0. We go to the next row. We now look at second row and third row. This guy here could be a leading one. So if we chose the second row to be the top row, quote unquote, then we go to step 4 now. This is already a leading one. So we want to make the entries below this 0. So we want to make this 0, which means we will apply again, or we will apply row 3 minus row 2. Correct? So in here, we are not changing row 1 again. So that's just 1, 0, 1. Then the other side there, you have 1, 0, 0. Row 2, we are not changing it. So we'll just copy 0, 1, 1, 0, 1, 0. For row 3, we have row 3 minus row 2. So 0 minus 0 there, it's 0. 1 minus 1 here, that becomes 0. Negative 1 minus 1 here, that becomes negative 2. And then in here, negative 1 minus 0 here, that's still negative 1. 1 minus 1 here, that's negative 1. 1 minus 0 here, that's 1. Okay? So now this leading one here, the entries below that is already 0. So now we move to step 5, meaning we start again the process from step 1. We only look at row 3. We want to make this a leading one. So look at this. We want to make this a leading one. We just multiply row 3 by negative 1 half. So negative 1 half times row 3. So if we do this, again, we are not changing rows 1 and 2. So we just copy that. 1, 0, 1, 1, 0, 0. Here we have 0, 1, 1, and then 0, 1, 0. For row 3 now, we have 0, 0, 1. That's negative 2 divided by negative 2. And then in here, we will have negative 1 times negative 1 half. That's positive 1 half. Similarly, for this, it's positive 1 half. And for this, we have negative 1 half. Follow so far? And now, we go to step 6. We now are on the backward phase. So this is a leading one here on the third row. We want all the entries above this third row become 0. Okay? So in here, we want to make this 0. What we can do is now to subtract row 2 minus row 3. Okay? At the same time, look at this. This is 1 and we want this to be 0. This guy here. So to make this 0, we also have row 1 minus row 3. So take note, I am not changing row 3 on these steps. It's fixed. What I'm only changing here are rows 1 and 2. So row 3 is fixed. Let's copy that. 0, 0, 1. And then I have 1 half, 1 half, negative 1 half. For row 2, so row 2 minus row 3, 0 minus 0, that's still 0 in here. 1 minus 0, that's 1. 1 minus 1, that becomes 0. 0 minus 1 half, we have negative 1 half. 1 minus 1 half, that's positive 1 half. 0 minus negative 1 half, that's positive 1 half. For row 1 here, row 1 minus row 3, you have 1 minus 0, that's 1. 0 minus 0, that's 0. 1 minus 1, that becomes 0. And then 1 minus 1 half, that's positive 1 half. 0 minus 1 half, that's negative 1 half. 0 minus negative 1 half, that's positive 1 half. And then you look at this. This is already your identity matrix. So what does this mean? This guy here will be the inverse of A. So A inverse, this is the matrix whose entries are this guy here. So you have 1 half, negative 1 half, 1 half, negative 1 half, 1 half, 1 half, 1 half, 1 half, negative 1 half. Okay? Questions? Okay? Let's have another example here. We want to find the inverse of the following matrix using inversion algorithm. So you have this. So you have this. So say this is your matrix B. You have the matrix B, invert it with, augment it with I. So if we rewrite this, we will have 1, 0, 0, 0, 1, 3, 0, 0, 1, 3, 5, 0, 1, 3, 5, 7. Augment this to the identity matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? For this particular example, okay, I will not completely follow the Gauss-Jordan um, the Gauss-Jordan method. Meaning, I will not, well, I will choose a certain row, but I will not put it on the top row and then make all other, uh, the, make the leading entry be equal to 1 and then convert all the entries below that leading one to 0. Okay? So we'll see how we're going to do this. So what I'm going to do is to start with this row 4. Okay? And then what I'm going to do is to subtract row 3 minus row 3. Sorry, I want to subtract row 4 minus row 3. Okay? So if we do that, we are fixing first row, second row, third row. We are changing row 4. First row, 1, 0, 0, 0. 1, 0, 0, 0. Second row, it's 1, 3, 0, 0, 0, 1, 0, 0. Third row, it's 1, 3, 5, 0, 0, 0, 1, 0. For the fourth row, I will have row 4 minus row 3. So in here, what I will get is 1 minus 1. This becomes 0. 3 minus 3, that will become 0. 5 minus 5, that will become 0 again. 7 minus 0, we have here 7. And for this, we will have 0 minus 0, that's 0. 0 minus 0 here, that's 0. 0 minus 1, that's minus 1. 1 minus 0, that's 1. Okay? And then I can divide this by 7. The fourth row, I can divide this by 7. I'll do it later. What I'm going to do now, subtract row 3 minus row 2. So subtract row 3 minus row 2. So row 1, row 2, and row 4, they will be fixed. We are just changing row 3. So for row 1, you have 1, 0, 0, 0, 0. Sorry, that should be 1 there. 1, 0, 0, 0. Row 2 will just be 1, 3, 0, 0, 0, 1, 0, 0. Row 3, it's row 3 minus row 2. So in here, you have 1 minus 1, that's 0. 3 minus 3, that's 0. 5 minus 0, that's 5. Of course, 0 minus 0, that's again 0. Here, 0 minus 0, that's 0. 0 minus 1, that's negative 1. 1 minus 0, that's 1. 0 minus 0, that's 0. For the fourth row, let's just copy this. So 0, 0, 0, 7, 0, 0, negative 1, 1. Okay? So let me copy this matrix and go to the next page. So we have this matrix. Then we can just now subtract row 2 minus row 1. So row 2 minus row 1. And again, I am fixing row 1. So I'll just copy this row here. 1, 0, 0, 0. 1, 0, 0, 0. For row 2, I'll have 1 minus 1, that's 0. 3 minus 0, that's 3. 0 minus 0, and 0 minus 0 there, it's just 0. 0 minus 1, that's negative 1. 1 minus 0, that's positive 1. And then you have your 0 and 0. Row 3 and row 4, you just copy. 0, 0, 5, 0. 0, negative 1, 1, 0. Here you have 0, 0, 0, 7. 0, 0, negative 1, 1. Okay? Our last set of steps here, second row, we divide it by 3. So 1/3 row 2. Third row, we divide it by 5. 1/5 row 3. Fourth row, we divide it by 7. 1/7 row 4. And first row, it's fixed. Okay? So what will happen to that? Well, in the end, we will have the identity matrix here. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. For this side here, first row is fixed. 1, 0, 0, 0. Second row, we divide it by 3. So you will get negative 1/3, negative 1/3 here, positive 1/3 here, and then 0, 0. Third row, we divide by 5. That becomes 0, negative 1/5, positive 1/5, and then 0. Fourth row, we divide by 7. So 0, 0, negative 1/7, 1/7. And this is your identity matrix. Therefore, this is the inverse of B. So I have written this as the matrix B, which means that B inverse is this guy here. 1, 0, 0, 0, negative 1/3, 1/3, 0, 0, 0, negative 1/5, 1/5, 0, 0, 0, negative 1/7, 1/7. Okay? Questions? Okay, so the remaining slides here are exercises. So in here, you have to find the inverse of these elementary matrices. Take note of that, elementary matrices. In here, suppose this is your EA. This is your E, and this is your A. You need to find the product EA. Okay? So use the theorem that was presented earlier. If you want to multiply out E and A, it's up to you, but it will take you a lot of time. Okay? What else? In this side here, well, you have this matrix. Find the inverse of this if it is invertible using the Gauss-Jordan elimination or using the inversion algorithm. Okay? And then you have to find the solution set of this homogeneous linear system. But I'll give you a hint. If you look at the coefficients here, you have 1, 2, 3, 2, 5, 3, 1, 0, 8. That's exactly this guy here. Okay? So, if you found that this is invertible, okay, if you found that this is invertible, then definitely you'll get the answer here immediately. Remember this theorem? If your A is invertible, AX equals 0 has only the trivial solution. So it means that if you found that this is invertible, then this system will only have the trivial solutions.